Actually, Imm is a method to improve the performance of a city, as an existing system, via modification of its constituents. In Imm, the city is not solely a mere aggregation of disconnected energy consumers, and the total energy consumption of the city is different from the sum of all of the building's consumption. This considerable gap between the total energy consumption of the city and the sum of all consumers is concealed from the urban morphology and urban form of the city. Imm investigates the relationships between urban morphology, energy consumption and environmental performance by focusing mostly on the subsystems characterized by physical characters and arrangements. Imm recognizes the city as a complex adaptive system comprised by the synergic integration of elementary parts, which through their arrangement and the architecture of their ligands provide a certain physical arrangement of the system. It's important to remember that CAS is a special class of complex system that has the capacity for adaptation and evolution through a dynamic between micro and macro-level feedback loops over time. Such systems consist of agents interacting in a non-linearly way. Through adaptation, agents have the capacity to locally synchronize their states or activities, and out of these local interaction, the system can self-organize with the emergence of coherent patterns of organization. Imm methodology is based on a multi-stage process, composed of 4 integrated phases, respectively: investigation, formulation, modification, retrofitting and optimization. Since this procedure represents a systematic transformation process, it is crucial for it to be structurally compatible with the nature of transformation in built environment. As a complex system, built environment is always subjected to change and at any stage produces new thresholds of transformation. Transformation in built environment adopts a non-linear form. The Imm procedure, too, is planned in a non-linear arrangement, accurate enough to cross different scales and flexible enough to maintain the capacity of the system to learn from itself. The process is initiated with the investigation phase. This stage involves a set of scientific inquiries into the urban system's structure and properties. Complex systems are recognized to be decomposable in their assembly and arranged in various levels, with a profound mutual relationship between their subsets. Accordingly, the performance of the system is being evaluated in the second phase, and intervention plans are being formulated. In the third phase, modification scenarios are being tested, with the same means that the actual context was investigated, and the last phase is dedicated to overall optimization, through the definition of local retrofitting strategies. Imm, a modification methodology based on identifying the morphology generators of the built environment's behavioral, investigating the linkage between the subsystems, investigating the logical interactions, investigating the hierarchy of scales. In Imm, city is a CAS, a specific type of the complex system with adaptive and resilience ability, and it's important to notice that the final performance of the complex system is different than the sum of its heterogeneous elements' performance. The generic morphological subsystems recognized by Imm are namely, urban built-up, urban void, types of uses, and links. The first 2 include all the physical elements, such as buildings, parks, roads. The latter 2 are the utilitarian elements like means of transports, jobs. It is necessary to note that the capacity of the system is resulted from fusing the physical and utilitarian elements together, There is relatively a small room for misunderstanding the morphological components, as defined here. However, as it was previously argued, the key to understanding the city as a complex system is not its reduction to its parts, but is having a deep inquiry into the relationships between parts. Now that the components are manifested, the question is how to study their fusing mechanism. According to this view, the city is not solely a mere additive result of the proprieties of the elementary parts, but city's structure emerges by a synergic integration of elementary parts recombined in a different way that make different organization emerging. Actually, emergence is something new that can't be described by the description of any elementary part propriety. Emerging properties are the product of the synergies between the parts. Actually, city is different than the sum of its elementary parts. But the configuration of the CAS is mostly described not just by elementary components, but by the correlation between them. By the architecture of the ligands, or how the system's components are interrelated depends the behavioral manner of the city. In vertical investigation, each of the four basic components has been asynchronously linked with the others and gave birth to a number of conceptual attributes named key categories. Key categories, hence, are bicellular entities of which each cell is one of the basic layers. By this definition, there is the possibility for 6 key categories to exist which have been identified by Imm as porosity, proximity, diversity, interface, accessibility, and effectiveness. In Imm, horizontal and vertical investigation are the first steps of the investigation phase. The designer activates disassembling procedure of the CAS into its basic physical components, such as voids, volumes, type of uses, and links. In the vertical investigation, the correlations will be investigated in a more specific way, through special features named key categories, with the role of decoding the patterns of integration that the basic components make with each other. In Imm, they are the final explanation for the morphologically propelled behavior of the spatial systems and important operational traits such as spatial configurations, functional arrangements, travel behavior, and the quality of movement are being justified through them. Key categories are types of emergence that show how elements come to self-organize or to synchronize their states into forming a new level of organization. Emergence is something new that can't be described by the description of the parts. Emerging properties are the product of the synergies between the parts. This process adds value to the combined organization. They're the products of the synergy between elementary parts, a new organization that emerged not simply as an additive result of the proprieties of the elementary parts. When we alter the interaction between elementary parts, recombining them in a different way, different organization emerges, but it also may be lost. It's important to focus on the fact that there could be various ways to conceptualize of urban elements fusing in an inclusive manner. One could be adding them up, one after another, and try to theorize meanings from the hierarchy of layers. Due to the fact that the number of basic components is 4, in this way the number of resulting key categories would be naturally 24. However, complex systems do not function in hierarchical orders. Accordingly, Imm suggests for the synergy of built environment elements to be studied on a non-hierarchical foundation formed by 2 of the urban elements followed by a hierarchical dynamism of the other 2. In this way, the number of possible key categories is cut in half. The operational facet resulting from build-ups and voids is a spatial configuration. The values related to spatial configurations are the ones involving the static distribution of spatial elements, such as build-up density, the ratio of public voids, etc. If the dynamism added to spatial configuration begins with types of uses, the resulting key category would be porosity, and if it begins with links, the key category would be permeability, which illustrates the quality of flow provided by given spatial configuration. With the same logic, other operational facets could be defined as dynamic density, street network, travel points, travel distances. The KC, the actual configuration and the characteristics of a specific urban CAS whenever considered in a provisional state, and effects of an endless transformation process became clear. Since the study's main concern is devoted to the urban morphology and energy consumption of the city, the involved subsystems and their specific correlation affects the urban form as well as energy consumption. The comprehension of the configuration of the involved subsystems and their links play a significant role in the Imm final result. Very scarce efforts have been done for systemic comprehensions and evaluations of the urban morphology through quantitative metrics. Imm synthesizes a new method for mapping and measuring urban morphology, based on reliable metrics by the use of qualitative maps, quantitative diagrams of correlated metrics and lists of indicators. Moreover, Imm results show that a multi-scale and multidisciplinary approach among systemic fields might help in finding ways and metrics to understand and describe complexity. For a better understanding of the metrics used to analyze in Imm, watch our tutorial on our YouTube channel, dedicated to the key categories and indicators. Porosity or void fraction is a measure of the void spaces in a material, and is a fraction of the volume of voids over the total volume, between 0 and 1, or as a percentage between 0 and 100%. In Imm, porosity emerges by the combination and the synergic integration of volume, void, links and type of uses. One can imagine the city as a solid porous volume, sponge-like, with various sizes of holes linked by linear void layer, whereby the integration of these two layers, urban volume and void, porosities. In general, porosity is a measure of how much of a solid mass is open spaces. This space can be between grains or within cavities. For a better understanding of porosity in Imm, watch the dedicated tutorial on our YouTube channel. In fluid mechanics, permeability is a measure of the ability of a porous material to allow fluids to pass through it. Permeability is related to porosity, but also to the shapes of the porous. In urban studies, permeability describes the extent to which urban form permit or restrict movement of people, or vehicles or material and material flowing. Imm considers permeability as a compactness attribute, which quantifies the level of organization of the urban texture, emerging from self-organized and synchronized states between the basic elements of the urban system. Permeability emerges by the combination and the synergic integration of volumes, links, voids, type of uses. For a better understanding, watch the tutorial on our YouTube channel. Diversity contributes to complexity and underpins system-level robustness, allowing for multiple responses to external shocks and internal adaptations. In Imm, diversity emerges by the combination and the synergic integration of volumes, type of uses, voids, and links. In order to investigate diversity, is crucial to define the key functions. They are divided in necessary and regular activities, such as educational facilities. On the other hand, the necessary occasional activities are the ones which the public prefers going when they need, not as a regular activity, as some government facilities or banks. Lastly, the optional activities are the ones as not strictly restricted, but as a choice of matter, as religious buildings, cafes and restaurants. In Imm interface emerges by the combination and the synergic integration of voids, links, volumes and types of uses. It is a strong indicator of the quality of movement provided by the street network, and a very important tool for design of an efficient urban morphology of street networks. Interface evaluates the transportation links in the network. It gives the precise information regarding the urban flow. In Imm, interface is assessed by the calculation of the mean depth for each individual link. Interface increases the complexity of the system by increasing the number of possible links to connect two nodes. For a better understanding of interface in Imm, watch the dedicated tutorial on our YouTube channel. In Imm, accessibility emerges by the combination and the synergic integration of volumes, type of uses, links, voids. Accessibility is the number of jobs of key functions area reachable within 20 minutes using different public transportation methods. The purpose of conducting accessibility analysis is because by the result we can understand the uneven distribution of key functions and transportation nodes, so that where the weaker parts in terms of not easy accessible area in the city could be spotted out. For a better understanding of accessibility in Imm, watch the dedicated tutorial on our YouTube channel. In Imm, proximity emerges by the synergic integration of links, type of uses, voids and volume. Proximity indicates how different types of uses can easily be reached by the non-motorized traffic. In other words, proximity is highly related to the pedestrian fruition of a space, the number of key functions type that one can reach in walking distance. Key function types are educational spaces, administrative services, entertainment, commercial, business. Despite the fact that the proximity is independent from the number of people and residents in the neighborhood, proximity of the neighborhoods could be explicated by the relationship between the number of job availability and the number of dwellings within the predetermined walkable distance. Watch the dedicated tutorial on our YouTube channel. In Imm, effectiveness emerges by the combination and the synergic integration of volumes, links, types of uses and voids. Effectiveness defines the capability of producing a desired result in terms of the transportation to cover built volumes around it. Simultaneously also defines the potential development within the intermediate scale. High accessible areas without any built volumes, which as a result become areas of potential development within the intermediate scale. An area with potential means that the transportation infrastructure exists without any volumes around. For a better understanding of effectiveness in Imm, watch the dedicated tutorial on our YouTube channel. The results of the synergic integration of the described key categories represents a second level of synergic integration (SLS) that makes emerging new pattern as properties of the city as CAS and represented as compactness, intricacy and connectivity. As briefly mentioned, the sustainable form could be achieved through a correct balance between the second level of integration, such as the compactness, the intricacy, and the connectivity. Any of them would not be sufficient on its own to achieve the sustainable form. However, the balance between compactness, Intricacy and connectivity is a foundation of a better performing and more sustainable urban form. The compactness of the city is defined by the synergic integration of porosity, permeability and proximity. How dense or diffuse is a city and how close or far different functions are within the city describe the compactness of a city. This morphological aspect has a great effect on the final energy consumption of the city. However, the compactness itself does not make a city or neighborhood sustainable. The combination of compactness, intricacy and connectivity can favor the creation of a more sustainable urban context. The intricacy of the city is defined by the synergic integration of interface, diversity and accessibility. How high is the level of integration of the entire system according to the spatial analysis considered concurrently with the level of diversity and how close or far different functions are within the city? It describes the level of complexity of a city. The connectivity of the city is defined by the synergic integration of accessibility, effectiveness and proximity. It draws attention to the connectivity aspect of the city. Connectivity is highly related to the transport of goods and data and plays a major role in the prevention congestion. The connectivity is the main issue to contradict who thinks that compactness is not sustainable form. They believe that the compactness lowers the efficiency of the system, triggered by the congestion of the data and objects. How does the complex adaptive system perform? Hence 12 families of indicators are used for achieving this result, and then the same indicators are used in the CAS retrofitting process, necessary for the final evaluation of the system performance, after the transformation occurred. It is important to emphasize that the 12 families indicators are also connected with the tools used to arrange later the structure of the system and called design ordering principles. Imm applies a list of 154 indicators, organized in 12 families specifically based on environmental themes but interlinked with other themes as social and economy. They are tools used in the Imm process for an objective measurement of the system's performance before and after the transformation. Diagnosis is the identification of the nature of a problem by examination of the symptoms made after examining. It is the final goal of the horizontal and vertical investigation based on Imm methodology. The image shows the graphic representation of the malfunctioning system of Porto Maravilha area in Rio de Janeiro. The black shadows, on the picture, is composed overlapping the graphics of Imm, as in an X-ray or computerized tomography. It shows the malfunctioning part of the system. A formulation phase anticipates the design phase, and it is highly connected with it. The main purpose of the formulation phase is to detect the transformation catalysts. The phase is dedicated to elect one horizontal component and one key category as catalyser of the transformation and consequently to let to the others the role of reactants. From the selection of one horizontal component and one vertical key category, the reaction of the system starts, driving the local modification and activating the system's transformation. It's clear that the choice of the catalyst depends on the investigation phase, and based on the conditions, components and key categories could play either the role of catalyst or reactants. Likewise, DOPE is an Imm acronyms for Design Ordering Principles. DOPs are descriptive guidelines to orient designers toward an awareness of systemic principles in the more complex problem areas being faced by design teams. They are also meant as guidelines to systems theorists to intimate or provoke more powerful theories of systemic and complexity for design, management, and other reflective practices. They are a net framework of integrated action that provide theoretically guidance for complex system design. They offer guidelines and a foundation to form a net framework enabling the integration of action for specific design contexts, ordering without centralized coordination. DOPs are tools used to arrange the structure of the CAS. In Imm, DOPs are not a fixed list of design recommendations, but a dynamic and active structure of integrated design principles every time arranged in consideration of the specific conditions of the CAS. They are specifically organized to deal with the weakness of the system, to modify the malfunctioning individual components of the CAS, responsible of its own actual performances. Therefore, rather than being a list of universal commandments, they address the issue locally, and by their local-oriented arrangement they lay the foundation of transformation. It is crucial to consider that the DOPs are associated with the environmental indicators, which are used for the assessment of the actual energy performance of the CAS. Imm Approach to Sustainability is aligned to the UN SDGs 2030. Accordingly, with our approach, cities are regarded as complex adaptive systems, and the focus is on simulating their operative mechanisms involving both the internal subsystems and the external systems that the cities are part of. The result will be a methodological interpretation of the SDG Number 11, suggesting locally based actions robustly linked with SDG indicators and evaluation methods. The SDG 11 is entirely about cities and human settlements, and making them inclusive, safe, resilient and sustainable. But in one way or another, all of the goals relate to work that happens in cities. So local authorities and the leaders who run them have a vital role to play in this global effort. The third step of the Imm is a design phase that applies a multi-layer and multidisciplinary approach. The aim of this step is to make possible the propagation of local changes towards the distant parts of the system, as a consequence of connectivity, and making this propagation the cause of a global change. Modification is driven by the modification of the horizontal and vertical catalysts, and the response of the reactants, which modifies the architecture of the ligands, thereby activating the reaction that transforms the structure of the system. Like in a chemical conversion, the catalysts catalyze the other reactants, adjusting the architecture of their joints and transforming the system structurally. The last step is oriented towards the evaluation of the performance of the new CAS, as a new energy-using complex system, which is comprised of modified subsystems in its own new formal configuration. Thus, this new configuration will become the new context, available for new transformations, since the transformation is an endless process. The new provisional CAS will be evaluated and compared with the old one, using the 12 families of indicators applied in the Step 1. After the retrofitting process, the last phase, local optimization, starts. Once the transformation has occurred, a new CAS measurement, as part of the retrofitting process, starts. The process is based on the comparison between the new CAS performance and characteristics, and the previous one. So, the last step of Imm is oriented towards the evaluation of the performance of the new CAS, as a new energy-using complex system, which is comprised of modified subsystems in its own new formal configuration. Thus, this new configuration will become the new context available for new transformations, since the transformation is an endless process. The new provisional CAS will be compared with the old one using the same investigation procedure Phase 1. A new vertical investigation of the new CAS modified by the design process will be repeated, to understand the new architecture of the links and how the new system's components, voids, build spaces, type of uses, links are now interrelated after the transformation process occurred. Then, the result of the vertical investigation, before and after the transformation, will be compared in order to evaluate their characteristic and the result achieved by the project transformation. Here an example of the retrofitting porosity. Then retrofitting permeability. And retrofitting diversity. Again retrofitting interface. And retrofitting proximity. Retrofitting accessibility. Retrofitting effectiveness. The new provisional CAS will be evaluated and compared with the old one, using the 12 families of indicators already applied in the first measurement of the CAS, before the transformation. This second measurement evaluates the environmental characteristic and performances of the new system, after the transformation process occurred. Thanks to these 12 families of indicators, it is possible to compare the characteristic and performance of the system, before and after the transformation process. Moreover, the indicators help to lead the complex system transformation in a correct way, as well as the result of transformation process. The main goals is to make the new system as effective as possible, obtaining a further implementation of its environmental performance, thanks to a further local transformation process subjected to constraints that are imposed. So, after the retrofitting process, a further phase named local optimization is considered. Of course, this minor and local change affects again the architecture of the system performance, modifying it structurally another time, but operating with a better control of the previous transformation's reaction. The final result of this optimization process is a concluding, but still provisional complex adaptive system, that configures itself as a new threshold of an endless transformation process. Thank you for your attention. We invite you to visit our website at www.indesignlab.com and our YouTube channel.